All right, so now we're ready to do our examples of volume by cross-section. And I am going to make it a little better for us this time. I'm going to let us math 9 our answers instead of integrating and doing all of the fundamental theorem and everything. We're just going to draw the picture, set up the function, or the integral, and then we're going to actually just math 9 it, put it in the calculator, and get the decimal answer. So I won't make us go through and make the video really, really long. All right, it says find the volume of the solid whose base is the region bounded by this function, the x-axis and the y-axis. So the first thing I want to do is draw a picture of this. All right, so negative 2x plus 3 is the y-intercept of 3 up here. It has a slope of negative 2. All right, so there's that. So there's that line. Okay, and then the x-axis would be down here, and then the y-axis. So we're talking about this area in here, that little triangle. Okay, so that's what we're talking about. That's the bottom, that's the base where we're going to build. All right, now the cross sections are going to be perpendicular to the x-axis. Woohoo! So I know if I'm perpendicular to the x-axis, I'm in x's. Okay, and then I want to put squares. So let's think about building squares perpendicular to the x-axis. So perpendicular to the x-axis. Oh, here's my x-axis. So perpendicular to the x-axis, this is going to be a square. And then there would be another square here. And then there would be another square here, right? Another square. So here's the length of the sides of my squares, right? Okay. So we're building squares on here. And we're in x's. So if we're in x's, I need to know our limits of integration, which is going to start from here, which will be 0, over to this point. So I need to figure out what is the x-coordinate right here. Well, it's on this line. So when does this line hit the x-axis? So when does this equal 0? So what's our x-coordinate? So that would be 1.5. So this is 1.5, because 1.5 times negative 2 would be negative 3, plus 3 is 0. So this will equal 0. This function up here will equal 0. It's just doing negative 2x plus 3. When does that equal 0? Because this is my y-coordinate. And I'm just solving, right? So negative 2x equals negative 3. Divide by negative 2, I got 1.5. So I'm just solving when that equation hits the x-axis. All right, so my limits of integration are going to be 0 to 1.5 because I'm in x's. And all I'm going to integrate is the area formula of what I'm building. So what am I building? I'm building squares. What is the area formula of a square? So it's side squared. The area formula of a square is side squared. All right, so that's what I'm going to put into the calculator. So what is determining the side lengths of this square? Well, whenever we determine lengths, it's always top curve minus bottom curve. So who's this top curve? Negative 2x plus 3 minus the bottom curve, which is the x-axis, which is 0. Because the x-axis is y equals 0. The y-axis is x equals 0. All right. So I'm doing top curve minus bottom curve. So top curve minus bottom curve is the length of each square. And I'm integrating from 0 to 1.5. And the area of a square is length times width, and they're both the same. So it's side squared. So top curve minus bottom curve, quantity squared. Then all you're doing is you're putting that in the calculator, math 9. So you math 9, type that in, and your answer you get is 4.5. So there's your answer. So I'm going to keep, I'm going to not make the video long, and I'm going to refrain from making us multiply this out, do the antiderivative, do the fundamental theorem, and all that. All right, so that answer is 4.5. All right, so for the next one, I kept the problem the same. So I kept it the same to make it simple. So it's negative 2x plus 3 is our line again. We know this is 1.5, this is 0, up here's 3. So this is our base area. So I kept all that the same. So now this time, for problem 2, I want us to do the cross sections perpendicular to the y-axis. So now we want squares still, but I want to put them perpendicular this way, perpendicular to the y-axis. So now they're going to be this way. All right. So, I mean, I could draw pictures like this and it'd look like that. Okay. So if they're perpendicular to the y-axis, that means when I integrate, I'm dy. So now I'm in y's, okay? So now I need my limits of integration to be y values. So I've got to go from 0 to 3 instead of going from 0 to 1.5. That would be x's. I need to go 0 to 3 because I'm perpendicular to the y-axis, so I'm in y. So I'm dy, okay? And so now I'm doing squares again. So squares were side lengths squared, because you always integrate the formula of what you're building. So the area of a square is the side length times width, and they're both the same number, so it's just side squared. So what's determining this, the length of the side of the square? Well, it's right curve, because I'm turned sideways, right curve minus left curve. So right minus left. So it's this function minus the y-axis, which the y-axis is x equals 0. But this is not in y's, okay? So I'm not going to do what I did last time to you. All right, we need to be in y's. So this equation is y equals negative 2x plus 3. So we need to be in y's. So I can't put negative 2x plus 3 in here because I need to be in y's. So I need to solve this for x. So let's move the 3 over. Y minus 3 equals negative 2x. Now divide by negative 2. So y minus 3 divided by negative 2. And if I just wanted to clean that up a little bit, that's going to be negative 1/2 y plus 3/2. So negative 1/2 y plus 3/2. Or if you didn't like fractions, negative 0.5 y plus 1.5, if you like that better. So negative 0.5 y plus 1.5. Okay, so that's the equation of this line. So when I do this length on my square, it's right curve minus left curve. So my right curve is negative 0.5 y plus 1.5 minus the left curve, which is the y-axis, x equals 0. So that would be 0. All right, so it is right curve minus left curve. So the line minus the y-axis, which is x equals 0. Okay, and so that's just integrating the side squared because we're doing a square. So it's the side squared, that's the area formula for a square, and we're in y's, so we're doing 0 to 3 instead of 0 to 1.5. And then we math 9 that, and the answer, and to math 9 it, you just enter all this stuff in. And so make sure you're practicing math 9 in this. And the answer is 2.25 when you enter that in the calculator for math 9. Now, typing this in the calculator, since we're in y's, you still use x's. So when you type it in the calculator, type in negative 0.5x plus 1.5 quantity squared and put dx. You don't put y's when you type in the calculator. The calculator doesn't care what letter you use. All right. So even though we're in y's on the problem, when you type it in the graphing calculator, type in x's. Okay. That's just a dummy letter. It doesn't, the calculator doesn't care what letter it is. All right, so now number 3, still I kept it the same. So I wanted to do multiple problems doing the same thing. All right, so our picture would be less complicated. So I'm doing negative 2x plus 3 again, the x-axis and the y-axis. So we're doing this triangle again. We're going to do cross sections perpendicular to the x-axis. Woohoo, we're in x's. So we're doing something dx because we're perpendicular to the x-axis. So this time I'm putting perpendicular to the x-axis. I'm going to do rectangles. So on this shape, I'm going to build rectangles perpendicular to the x-axis. And my rectangles are going to have a height of 4. So everybody that gets put on here has a height of 4. So we're doing rectangles. Rectangles are being built on here. But all the rectangles have a height of 4. Okay, so how do you integrate? Okay, first of all, let's put our numbers back on here. We're 0, this is 1.5, and this is 3. Okay, so since we're in x's, we want our limits of integration to be x values. So we need to go from 0 to 1.5. And then I just need to integrate the area formula of what I'm building, which is a rectangle. So I need the area formula of a rectangle. which is base times height or length times width, whichever way you want to think of it. So base times height. Well, I know every rectangle's height is going to be 4, okay? But what's the length or the base of every rectangle? Well, these are the bases of every rectangle, this distance here. So what's determining the length of each rectangle is top curve minus bottom curve, right? So that's going to be the line minus 0. So negative 2x plus 3 minus 0. And if you're tired of putting the minus 0, you can stop putting the minus 0. All right, but it's top curve minus bottom curve, top curve minus bottom curve, top curve minus bottom curve, top curve minus bottom curve. So it's always the line minus the x-axis, and the x-axis is y equals 0. So that's why it's the line minus 0. All right, so now you're ready to type that into the graphing calculator, math 9 that, and the answer is actually, the volume is 9. Turns out to be 9. All right. Next problem. I'm going to get them more and more interesting. Let's change it up a little bit. It says the volume of the solid whose base is the region bounded by x cubed. All right, so x cubed looks like this, right? That's x cubed, the little squiggly sideways S curve, right? I didn't draw him very nicely though. That's kind of an ugly x cubed. Oh, that's a little better. I just missed the origin. All right, we'll go with that one. All right, so there's x cubed, and then we're talking about y equals 0, which is the x-axis, and then x equals 1, which is a vertical line, okay? X equals 1 is a vertical line. All right, and then this intersects here on x cubed at the point 1, 1, so this is also 1 over here, okay? So we're talking about the region between x cubed, the x-axis, y equals 0, and the line x equals 1, which is the vertical line here. So we're talking about this region in here. So it's got a little curved edge here. It's not quite triangular. It's got a little curved edge here, and then a vertical and a horizontal. Okay? Now, what we're building on here are semicircles perpendicular to the y-axis. All right, so I'm perpendicular to the y-axis over here. So perpendicular to the y-axis, perpendicular to the y-axis, perpendicular, and we're putting semicircles on here. All right, so this is kind of like your little half caret, okay? Semicircles are a little half caret, okay? So what do we know? We're perpendicular to the y-axis. So when we integrate, the formula that we integrate, we're going to be dy because we're perpendicular to the y-axis, which means my limits of integration need to be y values. So I'm going from 0 to 1, which in this case, you would get it right whichever way you went, but always make sure you do y-axis if you're in dy. So 0 to 1. So now I'm going to integrate the formula of what I'm building on this region. So what I'm building is semicircles. So the formula for a semicircle is 1/2 pi radius squared, right? 1/2 pi radius squared. That's the formula for a semicircle because it's half of a circle. So 1/2 pi r squared. So we just have to figure out what's making the radius of each one of these little semicircles. Now, the trick is too, this is the diameter laid on here for the semicircle. So the radius is only half of this distance, right? So our radius is something divided by 2. So it's this entire distance divided by 2. So how do you calculate this entire distance? All right, this entire distance is going to be right curve minus left curve. Because remember, we're doing with respect to the y-axis. So right curve is 1 minus the left curve, which is our function. Now, this is not in y's. Remember, we're dy. So we need to rewrite this. Y equals x cubed. We need it in y's. So we're going to take the cube root. Okay? So x will equal the cubed root of y. So that's what this function is. X equals cubed root of y. So we use the function in terms of y. So cube root of y. So my radius, just let me backtrack a little bit. We're doing semicircles. So the formula for a semicircle is 1/2 pi r squared, because it's half a circle. So we need to figure out the expression for the radius. Your radius on each of these semicircles is only half of this distance between these two functions. So you're going to do right curve minus left curve, but that's this whole distance, and we have to divide it by 2. So right curve is this vertical line, which is 1, minus left curve, which is the parabola, not parabola, the cubic, but we have to put it in terms of y. So this is right curve minus left curve, and we have to take half of that because we only want the radius. So now we have 1/2 pi radius squared. So now we math 9 that. Let me find the answer. We math 9 that. And the actual answer, I'll tell you, is pi over 80, because I have that too. All right, if you do it longhand, pi over 80, and it's 0.039 is the actual answer if you math 9 it. So 0.039 is the answer when you math 9 that. So make sure you double check and make sure that you're math 9ing and know how to enter these correctly, and that you're actually getting the answer 0.039. Because if you enter this in and you don't get 0.039, then you're not typing it in correctly. So double check and make sure, pause this, take a moment, double check, type it in, make sure you're doing it right before you go on to number 5. So if you have to, pause my videos, of course, at any time when you need to double check something. All right, so I think this is the last one here, number 5. So we want to find the volume of the solid whose base is the region bounded by each of these 3 curves. All right, so this first curve is 1 minus x over 2. So that tells me we have a y-intercept of 1, and our slope is -1/2. Boom. So if my slope is -1/2, that means I'm going down 1 over 2. So this hits right here at 2, right? My slope is -1/2. So down 1 over 2. And then this other function is I have a y-intercept of -1. So I'm down here at a y-intercept of -1 and a slope of +1/2. So I'm up 1 over 2. So that means it's a line going this way intersecting at the same point. So this is the negative sloped line. This is the positive sloped line, g of x. And then we have x equals 0, which x equals 0, of course, is the y-axis. So then we got the y-axis in here. So we're looking at this triangular region right here. Okay, that's our triangular region that we're going to build something on. All right, so what are we building on there? It says the cross sections perpendicular to the x-axis. Well, we're perpendicular to the x-axis. So that means when I integrate, whatever I integrate, I'm going to be in x's. Okay, so looking at my problem over here, I'm going to go from 0 over to 2. Because I already know I'm in x's, I'm perpendicular to the x-axis, so I already know I'm going to go 0 to 2. I'm going to do equilateral triangles. Oh, good, there's that equilateral triangle. Okay, so remember the equation for the volume of an the equation for the area of an equilateral triangle is radical 3 over 4 sides squared. So that's all we have to do when you're doing cross sections. These are equilateral triangles, so I can even put one on here. So here's an equilateral triangle perpendicular to the x-axis. So I'm making it perpendicular to the x-axis, and then the triangle is standing up, perpendicular to the x-axis, perpendicular to the x-axis. So they're building like that. They're coming out of the screen towards us, and it's making this volume. All right, perpendicular to the x-axis. Okay, now the formula for the area of each one of these equilateral triangles is radical 3 over 4 sides squared. So these, whatever these side lengths are, all right, that's what we're going to square. So I'm going to put that in here, radical 3 over 4, and then side squared. So what's creating the lengths of the sides of these triangles? Okay, because all you're doing is integrating this formula, radical 3 over 4 sides squared. You always integrate the area formula of what you're building. Okay, so what's creating the side length of each one of these triangles? Well, this length is one of them. That length is the side of that one. This length is, so what's creating these lengths here? Top curve minus bottom curve. Top curve minus bottom curve. Top curve minus bottom curve. Okay, it's always top minus bottom, or if we're turned sideways, right minus left. All right, so the top curve is this line with the negative slope, which is this one. So that's going to be 1 minus x over 2. So it's going to be that curve minus the bottom curve down here, which is the negative 1 plus x over 2. All right, if you can read that, because that's kind of close together. Let me try a little better. I want to make it bigger. There we go. So this will be negative 1 plus x over 2. So we're looking at function f minus function g is what we got here. All right. So the one with the negative sloped line was function f. The one with the positive sloped line was function g. So this is function f minus function g. So top minus bottom. So that's what's creating the side length. So you square your side lengths and then you multiply by radical 3 over 4. You integrate that from 0 to 2 and it gives you the volume of the solid creating here. So I think cross sections are the easiest only because you just integrate the area formula of what you're building. And whatever you're perpendicular to tells you whether you're in X's or Y's. All right. And so then we can just math 9 this instead of multiplying it all out and doing the antiderivative and integrating fundamental theorem and all that. So if we math 9 this, let me see what the answer is when we math 9. And I think I got the answer if you do it longhand. The answer longhand is 2 radical 3 over 3. So that's what you get if you do that answer longhand. But if you math 9 it, you get 1.155. All right, so practice putting these in the calculator, math 9, and make sure you're getting these decimal approximations so that you know you can do this. All right, so I've given you several problems to try. There's some where the pictures are already there and you just write the integral and you can math 9 it. You don't have to do all the work. And then there's some where you have to sketch it like we did here. And then you have to write your integral and then math 9. So you've got both kinds where the picture's already there and somewhere you got to draw your own picture. So practice those. And if you need any more help or any more assistance, please get on Zoom during our asynchronous time. And then please tell me in the feedback form what you need more help on so that we can talk about things during our synchronous time. So go do some practice and see how you do.